Welcome to this tutorial on Kubernetes Liveness Probes. Liveness Probes are a critical component of the Kubernetes Health series. They enable automatic container health detection, ensuring your applications remain available and responsive. In this video, you'll learn how to configure probes that can automatically restart unhealthy containers, protecting your applications from failures and maintaining high availability. Liveness probes are periodic health checks that determine if a container is running properly. Think of them as the watchdogs of your containerized applications. When a liveness probe detects that something is wrong, Kubernetes automatically restarts the affected container. This mechanism is essential for protecting against common application issues like deadlocks, infinite loops, and unresponsive states. Without liveness probes, a container might appear to be running from the outside, but the application inside could be completely frozen or stuck in a broken state. Kubernetes provides 3 different types of liveness probes to suit various application needs. The first is the HTTP GET probe, which sends an HTTP request to a specified endpoint in your container. The second is the TCP Socket probe, which attempts to open a TCP connection to a specific port. And the third is the Exec Command probe, which executes a command inside the container and checks its exit status. Each probe type serves different use cases, allowing you to choose the best health check mechanism for your specific application architecture. To configure liveness probes effectively, you need to understand 4 key parameters. First is initial delay seconds, which sets the wait time before the first probe is executed after container startup. Second is period seconds, which defines the interval between consecutive probe checks. Third is timeout seconds, which specifies the maximum duration for each probe attempt. And fourth is failure threshold, which determines how many consecutive probe failures must occur before Kubernetes restarts the container. Properly tuning these parameters ensures your probes work reliably without causing false positives. Let's look at a practical HTTP GET probe configuration. In this example, the probe sends a GET request to the path /healths on port 8080. You can also include custom HTTP headers, such as a custom header with the value health check. The initial delay is set to 15 seconds, giving the application time to start up. The probe then runs every 10 seconds, with a timeout of 3 seconds and a failure threshold of 3 attempts. This means if the health endpoint fails to respond successfully 3 times in a row, Kubernetes will restart the container. The TCP Socket probe is simpler and works well for applications that don't expose HTTP endpoints. In this example, the probe attempts to establish a TCP connection to port 3306, which is commonly used by MySQL databases. The probe waits 20 seconds before starting, then checks every 5 seconds with a 2-second timeout. After 3 consecutive connection failures, the container will be restarted. TCP probes are particularly useful for databases, message queues, and other services where you just need to verify that a port is accepting connections. The Exec Command probe gives you the most flexibility by running a custom command inside your container. This example uses a simple command that checks if the file /temp/healthy exists using the cat command. The probe starts after a 10-second delay and runs every 5 seconds with a 1-second timeout. If the command fails 3 times consecutively by returning a non-zero exit code, the container is restarted. This type of probe is ideal when you need custom health check logic that goes beyond simple HTTP requests or TCP connections. To conclude, let's review some best practices for liveness probes. First, always set your initial delay seconds longer than your application's startup time. If the probe starts too early, it might kill containers that are still initializing. Second, keep your probe endpoints lightweight and fast to respond. Heavy health checks can consume resources and slow down your application. Third, carefully balance your failure threshold to avoid premature restarts. Too low a threshold might restart healthy containers experiencing temporary issues, while too high a threshold delays recovery from actual failures. Following these practices will help you build more resilient and reliable Kubernetes applications.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.